students, let's start today with the law of chemical equilibrium. So, this law of chemical equilibrium is a result that is obtained by applying the law of mass action to a reversible reaction in equilibrium. For example, if you consider a general reversible reaction, A plus B gives C plus D. At equilibrium, suppose the active masses of A, B, C, and D are represented as A, B, C, D. They are all in big brackets respectively. Applying the law of mass action, rate at which A and B react together, that is, rate of the forward reaction is proportional to active mass of A into active mass of B. And if I remove the proportionality sign, in place of that, a constant or proportionality comes represented by Kf into active mass of A into active mass of B, where Kf is called velocity constant for the forward reaction. Similarly, rate at which C and D react together, that is, rate of the backward reaction, is proportional to active mass of C into active mass of D, which is on removal of proportionality sign becomes a constant of proportionality is put there represented by Kb. So rate of backward reaction is equal to Kb into active mass of C into active mass of D, where Kb represents the velocity constant for the backward reaction. Now at equilibrium, we know rate of the forward reaction is equal to the rate of the backward reaction. Hence, Kf into active mass of A into active mass of B equals to Kb into active mass of C into active mass of D. You can see here on my screen. Or active mass of C into active mass of D upon active mass of A into active mass of B equals to Kf divided by Kb. Kf divided by Kb is equal to K. At constant temperature, as Kf and Kb are constant, therefore Kf upon Kb is equal to K is also constant at constant temperature and is called as equilibrium constant. Now keep in mind, by convention, the active masses of the products are written in the numerator and that of the reactants in the denominator part. Let's consider the general reversible reaction AA plus BB gives x to the power xx plus yy. So if you apply the law of mass action, we get active mass of x to the power x into active mass of y to the power y upon active mass of A raised to A into active mass of B raised to B is equal to K or Kc, where K is your equilibrium constant at constant temperature. And this mathematical equation is called as the law of chemical equilibrium and is defined as follows. The product of the molar concentrations of the products, each raised to the power equal to its stoichiometric coefficient, divided by the product of the molar concentrations of the reactants, each raised to the power equal to its stoichiometric coefficient, is constant at constant temperature and is called equilibrium constant. For gas phase reactions, that is, when the reactants and the products are gaseous, the equilibrium constant can be expressed either in terms of concentrations in moles per liter or in terms of partial pressures of the reactants and the products. If expressed in terms of partial pressures, it is denoted by Kp. Thus, if A, B, X and Y are gaseous in the above general equation reaction, we can write Kp is equal to Px to the power X into Py to the power Y, Pa raised to A into Pb raised to B, where Pa, Pb, Px and Py are the partial pressures of A, B, X and Y respectively in the reaction mixture at equilibrium. It may be noted that the pressures in the above equation are usually taken in atmosphere or bar or Pascal. Now let's see the relationship between Kp and Kc. Very important. The question comes, derive the relationship between Kp and Kc. Remember, at the end, we'll prove Kp equals to Kc RT delta N. So let's consider the general reversible reaction AA plus BB gives XX plus YY. And if the equilibrium constant for this reaction is expressed in terms of concentrations, we may write Kc is equal to X to the power X. Its active mass, big bracket will always write active mass of y raised to y divided by active mass of A raised to A into active mass of B raised to B, or simply Kc equals to Cx to the power x, that is concentration of x to the power x, into concentration of y to the power y upon concentration of A to the power A into concentration of B to the power B, where Ca, Cb, Cx, and Cy are the molar concentrations of A, B, X, and Y respectively. If A, B, X, and Y are gaseous, the equilibrium constant for the above reaction may be expressed in terms of pressure as Kp equals to Px, partial pressure of x to the power x, into partial pressure of y to the power y upon partial pressure of A to the power A into partial pressure of B to the power B. If the gases are supposed to be ideal, then we can apply the ideal gas equation, that is PV equals to nRT, or P is equal to N upon V into RT. N upon V is your concentration, that is molar concentration. It is number of moles per liter. Therefore, for the gases A, B, X, and Y, we may write partial pressure of A equals to Ca into RT, partial pressure of B equals to Cb into RT, partial pressure of X equals to Cx into RT, and partial pressure of Y equals to Cy into RT. Where T is your temperature, R is your gas constant, and C is the molar concentration of the gases A, B, X, and Y respectively. Hope till here it's clear. Now, when you put these values in equation 2, we get Kp. When we are putting these values, we get Kp equals to Cx RT to the power x into Cy RT to the power y divided by Ca RT to the power a into Cb RT to the power b. On solving this, we arrive at Cx to the power x into Cy to the power y, Ca to the power a into Cb to the power b. Here you see RT x plus y, and since RT is common, we bring this term a plus b on the numerator part, and it becomes RT raised to x plus y minus a plus b. So this x plus y minus a plus b is represented here by delta n. So we get the relation Kp equals to Kc RT delta n, where delta n is equal to x plus y minus a plus b. That is number of moles of gaseous products minus number of moles of gaseous reactants. That is equal to change in the number of moles of gaseous substances. So we get the relation that is between Kp and Kc as Kp equals to Kc RT delta N, where delta N equals to x plus y minus of A plus B. Now look at this numerical problem. The question is, the following concentrations were obtained for the formation of ammonia from nitrogen and hydrogen at equilibrium at 500 Kelvin. Molar concentration of nitrogen is given here as 1.5 into 10 raised to minus 2 molar. Concentration of hydrogen is equal to 3 into 10 raised to minus 2 molar, and for ammonia it is 1.2 into 10 raised to minus 2 molar. Calculate the equilibrium constant. So this is formation of ammonia. So write the well-balanced equation first. N2 plus 3H2 gives 2NH3, reversible reaction. And Kc for this reaction will be equal to product of products divided by product of reactants. And the coefficients which are there, they will be raised to their powers. As in this example, Kc is equal to NH3 to the power 2 divided by N2 into H2 to the power 3. So NH3 value is given here in the question as 1.2 into 10 raised to minus 2. So 1.2 into 10 raised to minus 2 square divided by nitrogen value is given here, concentration as 1.5 into 10 raised to minus 2. So divided by 1.5 into 10 raised to minus 2 into hydrogen concentration is given here as 3 into 10 raised to minus 2 molar. So 3 into 10 raised to minus 2 cube. And on solving this, I get the value of equilibrium constant Kc as 3.55 into 10 raised to 3. So this is how you'll solve the equilibrium questions. And it's very easy to solve. Next, look at the next problem. The problem is, at equilibrium, the concentrations of nitrogen is equal to 3 into 10 raised to minus 3 molar. Oxygen, it is 4.2 into 10 raised to minus 3 molar. And NO equals to 2.8 into 10 raised to minus 3 molar in a sealed vessel at 800 Kelvin. What will be the value of Kc for the reaction? N2 plus O2 gives 2NO. So here again you will write Kc is equal to NO to the power 2 upon active mass of nitrogen into active mass of oxygen, and put the values and calculate the value of Kc. So as I said, Kc is equal to active mass of NO to the power 2 divided by molar concentration of nitrogen into molar concentration of oxygen. On putting the values, 2.8 into 10 raised to minus 3 square upon 3 into 10 raised to minus 3 into 4.2 into 10 raised to minus 3. So molar square and here molar square gets cancelled, and we get the answer here as 0.622. No unit is there, unit is cut. Let's look at next problem, and it is PCl5, PCl3 and chlorine are in equilibrium at 500 Kelvin and having concentration 1.59 molar PCl3, 1.59 molar Cl2 and 1.41 molar PCl5. Calculate Kc for this reaction. PCl5 reversible sign, PCl3 plus Cl2. So Kc is equal to molar concentration of PCl3 into molar concentration of Cl2. It is into, remember it is product. So into PCl3 active mass into Cl2 active mass divided by molar concentration of PCl5. So we get, on putting the values 1.59 square upon 1.41, I get the answer there as 1.79. So these type of problems are very easy to solve. Look at this problem. Just now I dealt with the relationship between Kp and Kc, and I said Kp equals to Kc RT delta N. So look at this problem 7.5. The question is for the equilibrium 2NOCl gives 2NO plus Cl2. All are present in gaseous phase. The value of equilibrium constant Kc is 3.75 into 10 raised to minus 6 at 1069 Kelvin. Calculate the Kp for the reaction at this temperature. So as we know the relation Kp equals to Kc RT delta N. And for this reaction, if I need to calculate the value of delta N is number of moles of gaseous product. So here you see 2NO plus Cl2, 2 plus 1. So number of moles of gaseous products are 3 here. 2 plus 1, 3. Minus number of moles of gaseous reactants it is. So here it is 2. So 3 minus 2, the value of delta N comes out to be 1. So I need to calculate Kp. Kp is equal to Kc. Kc is given here as 3.75 into 10 raised to minus 6 into R value will take here as 0.0831 into temperature here we consider as 1069 Kelvin. So on solving this, I get the value of Kp here as 0.033 respectively. That's how I'll be solving these problems. Now see the value R, where I'll be taking which value of R. Keep in mind, if the partial pressures are taken in atmosphere, that means the value of gases which are given, partial pressures if it is given in atmosphere, the value of R to be used in the equation will be 0.0821 liter atmosphere per degree per mole. 0.0821 liter atmospheres per degree per mole. Temperature of course will be there in degree Kelvin. If pressure is expressed in bars, then the value of R which you would take is 0.0831 liter bar per Kelvin per mole. I repeat, pressure expressed in bar, the value of R which you will consider is 0.0831 liter bar per Kelvin per mole. And if the given value of Kp or Kc is dimensionless, we'll take the value of R as 0.0831 liter bar per Kelvin per mole as we considered in the above example. So there Kp Kc was dimensionless. So we took the value of R there as 0.0831 liter bar per Kelvin per mole. Now let's consider the characteristics of equilibrium constant. First characteristic is the value of the equilibrium constant for a particular reaction is always constant, depending only upon the temperature of the reaction and is independent of the concentrations of the reactants with which we start or the direction from which the equilibrium is approached. For example, if you consider the reaction between acetic acid and ethyl alcohol at 25 degrees Celsius, the equilibrium constant Kc is found to be 4 for the reaction. So Kc is equal to molar concentration of CH3COO C2H5 into molar concentration of H2O divided by molar concentration of CH3COOH into molar concentration of C2H5OH, which is equal to 4. So this is the first characteristic of equilibrium constant. The second characteristic is if the reaction is reversed, the value of the equilibrium constant is inversed. You can take the example. If I reverse the equation, CH3COO C2H5 plus H2O gives CH3COOH plus C2H5OH. The value of equilibrium constant K dash C is equal to 1 upon Kc, inverse of it, which is equal to 1 upon 4, which is 0.25 at 25 degrees Celsius. So this is the second characteristic feature of equilibrium constant. The third characteristic is if the equation having equilibrium constant K is divided by 2. The equilibrium constant for the new equation is the square root of k, that is root over k. You can take the example N2 plus 3H2 gives 2NH3. Then for the reaction 1 by 2 N2 plus 3 by 2 H2 gives NH3. The value of equilibrium constant K dash is equal to root over K. It is obvious K equals to NH3 square divided by molar concentration of N2 into molar concentration of H2 to the power 3, and K dash is equal to NH3 divided by N2 to the power half into H2 to the power 3 by 2. So we get here K dash is equal to root over K. The fourth characteristic feature is if the equation having equilibrium constant K is multiplied by 2, the equilibrium constant for the new equation is the square of K there. So it is the square of K square. You can consider an equation. If an equation is multiplied by n, the new equilibrium constant is equal to K raised to n. For example, if the equilibrium constant for the equilibrium reaction H2 plus I2 gives 2Hi is K, then n moles of H2 plus n moles of I2 gives 2n moles of Hi. Equilibrium constant is equal to K raised to n. The last characteristic feature is if the equation having equilibrium constant K is written in two steps having equilibrium constant K1 and K2, then K equals to K1 into K2. You can consider the reaction N2 plus 2O2 gives 2NO2. For this reaction, K equals to active mass of NO to the power 2, NO2 to the power 2 divided by active mass of nitrogen into active mass of oxygen to the power 2. So this reaction, let it take place in two steps. First step is N2 plus O2 gives 2NO and 2NO plus O2 gives 2NO2. So K1 for this reaction is NO to the power 2 divided by N2 into O2. And for the second step, K2 is equal to NO2 to the power 2 divided by NO to the power 2 into molar concentration of oxygen. So K1 into K2 is equal to K according to the equation 1. And we can summarize these characteristics in the table given below. When the equation is reversed, the new equilibrium constant is 1 by K inverse. When the equation is divided by 2, the new equilibrium constant is root over K. When the equation is multiplied by 2, the new equilibrium constant is K square. When the equation is divided into two steps, the new equilibrium constant is K equals to K1 into K2. And the last characteristic feature is the value of the equilibrium constant is not affected by the addition of a catalyst to the reaction. Why? Because the catalyst increases the speed of the forward reaction and the backward reaction to the same extent. That's why the value of equilibrium constant is not affected by the addition of a catalyst to the reaction. Hope you have understood these points. And in the next class, we'll be dealing about the homogeneous and heterogeneous equilibrium in detail and the applications of equilibrium constant. Till then, thank you children and have a nice day.